In this video, we're going to start looking at modern atomic theory, starting with the Bohr model of the atom, which in itself is not modern, but it's going to lead us to a more modern model of the atom. The Bohr model is the typical atom. When somebody's asked to draw an atom, they usually have this nucleus in the middle, and then they've got these rings around the outside with electrons flying around, which we know is not 100% accurate, but it's better than previous models where the electrons were just randomly flying around the nucleus. Now the Bohr model puts those electrons in specific energy levels, and here's kind of where we get that evidence. You may be familiar with a prism, which is something that will separate light into all its individual colors. So, for example, visible light can be separated into all the different colors that would be present in a rainbow. Pretty awesome, right? Now, if we do this to a particular element, and you may remember from first year chem, in class I'll show you these different tubes of gas. We call them emission tubes. You hook them up to an electricity source, and in a sense you're like electrocuting the atoms, you're giving them a spark of energy, and we say that those atoms become excited, they gain energy. And it could be from electricity, or in the lab. You may remember doing a lab where you heat different ionic salts and the flame is different colors and it represents different metals. That flame testing lab, everybody always loves that because you're burning a bunch of stuff. And what makes that more fun? When things burn in different colors. I mean, it's a blast. So here we've got these excited atoms. When we add energy, the electrons jump to a higher energy level. And we say they're excited. Now we should make note that excited is not stable. High energy is not stable. These atoms do not want their electrons excited. They want their electrons at their home base, or what we call ground state, where it's where the electron is normally found. Well, in order to do that, if I have an electron that becomes excited and jumps up to these high energy levels, he's got to release that energy to get back down to the ground state, the lower, more stable energy level. Often, that energy is released in the form of light. And that light may have different wavelengths. And we can use those wavelengths of light as an indicator as to what might be exactly happening to those electrons, which is totally wild because we can't see atoms, we can't see electrons, but yet we kind of have evidence that supports this idea of electrons gaining energy, moving up and down the energy levels, falling back down to the ground state, releasing different colors of light. Now here's kind of a good visual, and you might remember this one from first year chem too. So we've got these emission tubes, these tubes that are filled with gases. Here's hydrogen. Do you remember wearing those prism glasses? We'll do this in class too. It's awesome. Everybody looks super cool wearing these prism glasses. If you look at the hydrogen tube, we hook it up to the electricity, we electrocute these hydrogen atoms. It kind of glows in like a pinkish purple color, but when we shine that light to the prism glasses, it gets separated into these specific bands of light, these specific colors. And from there we can speculate as to what might be happening, in hydrogen's case, to his one little electron. For example, let's say that one little electron, here he is, he's in energy level 1. Let's say he just gains a small amount of energy. So he jumps from level 1 to maybe level 2. Well, he still doesn't want to be in level 2. His ground state is level 1. So he eventually wants to fall back down to energy level 1. Well, in order to do that, he's going to need to release all the energy that he originally gained to go from level 1 to level 2. He'll release that energy in the form of light. And since we only made a small jump, to go from level 1 to level 2, we probably just gained a small amount of energy. Then we'll release a small amount of energy. So we might see low energy colors. Like in this case, maybe we'd see red light. And you might remember that there are specific elements that give off kind of a red or crimson colored flame when you look at a flame test. So we can speculate then that the electrons are maybe just gaining small amounts of energy, because then when they fall back down to the ground state, they're releasing small amounts of energy. Let's put that term in too. You probably remember it, but the home base is called ground state. For hydrogen, we only have one electron, so it's definitely the first energy level. In other atoms that may have more electrons, ground state is just where that particular electron would normally be found. So it could be that the ground state is level 2 or level 3, the normal home base for that electron. When you look at the emissions from a hydrogen atom through the prism, you will see a really nice red band. So we can tell sometimes that electron is just making small jumps, releasing low energy red light. You'll also usually see kind of like a purple violet band of color. Sometimes that one electron gains a larger quantity of energy, so he jumps up to a higher energy level. And let's pretend he's jumping from level 1 to level 5. Well, he certainly doesn't want to be in level 5. That's not stable. He wants to fall back down to the ground state, level 1. Well, this time he must have gained a high amount of energy to go up to level 5. So when he falls back down, we're going to release high energy, which might translate into like a violet or a blue color of light. I'm thinking about the Roy G. Biv rainbow. So you'll see kind of like it's like a purple colored light when you look at the hydrogen emissions. You'll also see kind of like a teal or green colored band. And these three bands make up what we call the bright line emission spectrum. It's specific bands of color that are produced for a specific element. It's a specific pattern of colored bands. And we'll look at a few of them in the lab and in class. It's pretty awesome. It's a way of identifying an unknown element because no other element would form the same bands of colored light as, for example, hydrogen in this case. There's an example in here. It's not colored, unfortunately, but it's trying to show these bands of light, the bright line emission spectra of different elements and an unknown. And this unknown might be a mixture of elements. To identify the elements present in that unknown, we would just match up the colored bands. Now obviously here they're not colored, but they are in specific patterns. So all I need to do is look at these pattern bands, and I want to match them up with my unknown. So it looks like my unknown, there we go, must have helium. These match. Helium, those match. Yep. We definitely have helium. And it looks like the other one. Oop, I bet it's this guy. I bet it's hydrogen. Yep. Hydrogen. And here's these last two bands. We'd match them up. So hydrogen. So again, this could be obviously colored if I was looking at real data in the lab. But here it's just patterns. And they may do this on a multiple choice question and say A, B, C, D, E, F, G. Which elements are present in the unknown? And if it's not colored, then I'm just trying to match up these patterns of bands that would be colored from real lab data.